Make sure you did like Teo did here and actually write this. Or you could say the limit of the terms. That would be clear to me. You could actually write in English. The limit of the terms is -5, which is not 0. Therefore, by the nth term test, this diverges. Something like that would be fine too. Anything correct is okay, of course. But yeah, you should have those elements in there. Name the test you're using. Say that it diverges. If you're using the nth term test, then you should say what the terms go to. And say that that's not 0. So that's, I think, my statements on A. B is over on the whiteboard over here. And I think all the elements are present there for the direct comparison test. The first order of business for B is to identify the rule, which Shoam did here or here. Okay? And notice that can be compared to 1 over n squared, which converges. This is always less than that, so I think we're good. But all these, look at all the elements. You need to identify the thing you're comparing it to. You need to say that it converges and why. You need to talk about the comparison you're making. I think this is actually somewhat critical too, because it's not obvious that two algebraic expressions, I mean, what do we mean? We mean on the domain of interest. In fact, some of these ones we've worked with yesterday and today here fail for like negative n values, right? It's actually maybe not true for a negative n value. So you do need to be a little careful here. So I would just say that it's true for the values we care that it be true for. And then finally we can make our statement. Make sure you mention somewhere the direct comparison test. C, I don't have much to say about. It's just geometric and is that, I don't know, what is there a nice way to write that without using a calculator? What would that be?
It's 10 over 1 minus pi over 5.
So yeah, the sum would be like 50 over 5 minus pi, right? Would be one way to write that. And D will come back to because we haven't done the ratio test, and I think that's what we need to do that one. So put your finger in your warm up, and we'll come back to that. Okay? Promise in a few minutes. Yeah.
How do you? I forgot how to write the limit for a series. Could you remind?
I mean, this is the way you do it right here.
Wait, so you don't have to write LIM?
Well, you could. The place where it would go would be here. You would write like the limit as like capital M goes to infinity of the sum from n equals 1 to capital M of 10 times pi over 5 to the n minus 1, right?
You also use n?
I wouldn't use little n again because it's here. That would be confusing, right? So what this says is sum this up to the number capital M and tell me what you get. And now take the limit of that top number until it gets to infinity. But we don't want to use the same variable in both places, maybe, right? So that would be, if you're dying to use the lim, then that would be how you'd write that. This is, in fact, what this means when we have that at the top of the sum. Yeah. Oh, okay. Can someone just refresh our memory about how we evaluate the limit of the terms? We are not talking about series at all right now. All we're talking about is the terms themselves. Teo probably knows, given that he did the problem. Noah, you want to explain?
Sure. So you, I guess, simplify the expression on top. So it's -5n cubed, or plus 2. And since you have -5n cubed over n cubed, it's like taking the horizontal asymptote of the equation, right? And you're going to get the limit at -5. And the nth term test says if it doesn't go 0, then you're going to have a series that diverges.
That was well said. Well, do you have any questions for Noah? Well, some key words I heard him say in there were like horizontal asymptote. He also talked about rearranging the numerator because I wrote it in a way that maybe isn't comfortable for you, right? You might like to see it more like -5n cubed plus 2, right? And then it's just the rules for horizontal asymptotes for a rational function, which is what this is, right?
So we don't really need to know that.
Yeah, evaluating the limit of a sequence, that is the limit of the actual terms, is pre knowledge, right? You should already know how to do that if it's from whatever you know about the different functions that might be involved. To some extent, I mean, there's still could be sums that are tricky, but that's just a rational function, right? So wouldn't you agree the horizontal asymptote is y equals -5 for that function. That's what the terms get closer to then, and then get large. Yeah.
For the bottom one, I know you said they were not going to have done that yet.
Yep, you're not allowed to talk
Does
about
it
it.
converge?
It may converge. Yeah, maybe.
Okay.
Okay. There's our review. It's top secret right now.
That's bigger than whatever squared if it's larger than 4? Or is that just like a coincidence? The factorial, like, if you do like n squared, n factorial, the factorial is only bigger than the squared one, and is bigger than...
Yeah, n factorial does grow. But what about the 2? Wasn't there a 2 to the n in there too or something?
2 what?
Wasn't there also like a 2 to the n in there too?
Yeah.
So how does that affect things? I don't know. We'll look at it. We will do that problem. All right, this is where we stopped yesterday. I'd like to say a little bit more about the limit comparison test. Do one more example of it at least, and then we need to say something about the ratio test as well. So remember we did this example. We talked. I think we're just kind of rushing at the end there. What did I just do? I don't know. The idea again is that we'd like to show that a function that we're looking at right now that's brand new to us grows in exactly the same way relative to some other known function. And once we can establish that, then if one of them diverges, the other does too. And if one of them converges, the other must too. If they grow at the same rate, then that's our conclusion. And the way we might quantify and make rigorous this idea of growing at the same rate is if we stack them, like we have down there at the end, and we take the limit of the stack, it should come out to be a constant. If it comes out to be 0, refresh my memory, what does that mean? If you have two functions you've stacked on top of each other, and as you go out to infinity, it gets closer to 0, then what does that mean about the growth of the two functions? Which one grows faster? The bottom one. Well, that's not what we wanted. We wanted to show that they were equal in growth. If we get infinity, that's also not good, because that means the top one was growing faster. Also not what we wanted. So if that happens, no big deal. Just pick a better function, right? It's just inconclusive, right? We just need to pick a better function. Our goal would be to get, when we do the limit, a constant, like here we got 1, right? So sometimes that's pretty clear. Like clearly, even before you start, you're probably thinking, yeah, this grows basically exactly the same way as 1 over n to the 4th does, this function. With the -3, we all have a sense for that. It doesn't really mean anything, right? Out of infinity, who cares that we're subtracting 3? So our intuition is strong there. Our intuition might be not quite as strong initially on one like this, though, right? Like, I don't know. So maybe it is. Think about it for a second and see if you can come up with a function that this grows, because then we'll run the test on it here, and we'll stack them. But I need to think about which function I'm going to stack this with. What do you think this grows like? Yeah, you can't really simplify the bottom in any way with, like, but you just shoot from the hip maybe too then. I mean, just go by feel here. Work with your intuition. Feel free to do some questionable algebra. Whatever. Just give me what you think this grows as. I mean, is this like on the order of like 1 over n? Is this on the order of 1 over n squared? 1 over the square root of n? Yeah.
I would say it converges because the bottom is, the top goes to n, but the bottom one goes to n to the 3 halves.
Okay.
Which is,
Okay.
it should get slightly larger.
Yeah, we're trying to think about which of the, in particular, which of the p series that we introduced yesterday, 1 over n to the what, do you think this grows like? Ignore the -1 maybe, right? Are you feeling like that doesn't matter out of infinity? Like I think out of infinity this basically grows like this does. Agreed? I think that actually is a p series, isn't it? You just need some work on it. What is it? Yeah, see, you love it.
1 over root n.
It is actually. Let's see if we can convince ourselves of that. That's what you said, Maddie. But
Oh no.
yeah. So now, before we even go anywhere else, I do agree that the terms themselves go to 0. So if someone asked, to use the nth term test here. The nth term test is inconclusive. The nth term test is inconclusive. Why here? And the terms go to 0, don't they? But that doesn't really mean anything necessarily. We've realized that just because the terms are going to 0, that's necessary for sure, but it is not sufficient to show convergence. So the nth term test doesn't really help us. But maybe this limit comparison test, maybe if we really claim that this grows the same way as this, maybe we could show that using the limit comparison test. So here we go. All right, so how does this work? We say something like, since this series, what does it do? Diverges or converges? Diverges. Why? Because p is a half, which is less than, strictly, than 1. And now here it comes, right? The limit as n goes to infinity of, how do you want to stack these? How about 1 over n to the 1/2 on top over, I mean, just like going in faith here, hoping that this in the end comes out to be a constant. Let's hope that that's true. If not, then like I've got an eraser and like I can use it. Okay. All right, I think we're all comfortable with like doing a little flip here to make this look a little bit better as one fraction instead of a big stack, so that we get what? The cube root of n, excuse me, the square root of n cubed minus 1 over n times n to the 1/2. Feel free to race ahead of me here. What's going to go on here? I mean, what we say the denominator?
So, like the n times n 1/2, that's like 1 plus 1/2, which would be 3/2.
Okay, you know how to add.
Yeah.
Good job. Okay. So, AKA, yeah, n to the 3/2 in the denominator, which is square root of n cubed. Is that okay? And I also happen to know another property, maybe you know too. The square root of a over the square root of b is equal to the square root of a over b. And now, forget the square root for a second. As n grows large, what does the radicand do? As the value of n grows large, what does the stuff inside the radical do? Okay, it approaches 1, right? Using machinery that Noah explained earlier in the period, right? It's just partial asymptote. So if this function here approaches 1, then the whole thing approaches the square root of 1, which is, let me get my calculator out. Oh yeah, that's right, 1, okay. So I think, are we convinced that we did the job? That in fact this is 1, which means that they do grow at the same rate relative to one another? Which means that if one of them does one thing, then the other does too. So what's our conclusion here? Okay, Maddie. You're going to destroy my flow, but go ahead.
How did you get from the since to the thing right next to the and? What did you multiply and divide it by? I'm not totally clear.
This, here, you mean? Yeah, so the limit comparison test says, hey, stack the two of them. Do one over the other in either order, actually. This is the one that we have, and this is the one that we think that it grows on the same order as. We think that this acts like 1 over n to the 1/2. Because of our thought process earlier, we think that this has the same behavior as 1 over the square root of n. So stack them in either order you like. And by the way, remember, if you pick the wrong thing to go up here, it's fine. In the end, you'll get something different than 1. You'll get 0 or infinity. And then you'll be like, oops, try again. But it happens to be true that we picked the right one. The reason I know we picked the right one is we did some algebraic work here. We evaluated the limit and we got a number that's not 0 or infinity. Yay. Right? Yes?
By picking the right one, do you mean like switching them, or like you pick the right function?
Oh yeah, it shouldn't matter whether we have them on top or bottom. That's not a choice that matters. Like we'll still get 1 at the end here if you had it stacked the other way. No, the choice I'm talking about is that we picked 1 over n to the 1/2. Like if you had picked 1 over n, for example, you would have gotten 0 or infinity at the end. Try it if you don't believe me. And it's not a problem. It's just inconclusive. You need to try something better. Yeah. The homework tonight is to go back and revisit 3 and 4 and do them all correctly. And do 10 more challenge problems. Okay? Bye. Good luck. All right. Wait. Hold up. Don't. All right. So, we need to say that 1 is in the interval 0, the open interval 0 to infinity. So the series converges. Diverges. Excuse me. By what? By the LCT. Yeah, that's right. That's what we were doing. Okay. So that's good. I mean, I think we've got a little bit of better handle on the limit comparison test, and now we need to talk about the ratio test here. And yeah, I really would expect you to write all this, right? Like, I think every element of what I've written is a critical one in justifying why this diverges. Isabel.
If you ever had like a big thing on the top divided by a big thing on the bottom, could you not bring in something else and just use the two on the one on the top and the one on the bottom, and be like, so the top one diverges and the bottom one diverges too, and the whole thing should diverge, or no? Are you not allowed to do that?
Well, the whole thing, I mean, I think you're thinking of like if you have, 1 over n and what's another one that you think, or what do you say? What do you get?
1 over n and then like 1 over n to 1/2 or something, and yeah, or something.
Okay, so
Like prove that.
that'll go to 0. Do you see why?
Okay.
Yeah, that goes to 0.
It's a bad example. But like.
But you want it to go to 1 instead?
Yeah, like
Okay.
if you have like something on the top and then something on the bottom, and they like pretend they went to 1.
Okay, like I can do that by making this like, how about n plus 2 or something?
Yeah.
That goes to 1?
Could you say that the whole thing diverges?
No, the whole thing goes to, you mean, I mean, the whole thing goes to 1. So are you thinking of like the series, this as a series
Yeah.
now?
Yeah.
I mean, that's a completely different question.
Oh.
But you're interested in asking it, you said? So explain why that definitely diverges if the limit of the terms is 1. You just said it would.
It's just the end.
Then it's the term test. So let's not fill people's brains with that. But it was an interesting question. Okay. All right. Let's talk about the ratio test. It's right in front of you on your paper. So pull it out and have it in front of you. It should be exactly how you see it here. Yeah, show.
Just a question. So the last problem, in a test situation, how long do you leave someone to say on
4 minutes. I made that up. But right? Yeah, I wouldn't expect it to be instant. All right, take like we've done before. Maybe you've read it, but let's kind of read it again in your mind, and I'll give you like just 30 seconds to think about what it says, what it means, and maybe even why it's true. Maybe you can even think about why it's true. My first observation, if I'm you, is probably that this looks a little familiar, especially this language down here and the use of R. What does it remind me of? Yeah, I mean, this just feels like the geometric series test, doesn't it? I mean, we're even using the letter R, and down here, this result sounds very familiar to me too. Okay, and that's not a bad intuition to have. In fact, that's That's kind of the cue we're taking as we think about what this means. In order to fully understand what this means, you need to also remind yourself that by a sub n plus 1 and a sub n, we mean the entire rule for the next term and the current term, right? So even though this looks cute and small right now and compact, in reality, like the last example with the limit comparison test, we're going to be stacking two rules. It's going to actually come out to be something kind of a little bit terrible, at least at first. We'll simplify it very quickly, but so this expression, it could be a little bit daunting to work with, but we'll work with it nonetheless. Okay, so the idea is on this, see if this reckons with what you just read and understood, that we're looking at the ratio, the limit of the ratio between terms as we go out really far. And we're saying that if that equals a constant, then basically, even though the series may not be geometric, it acts like a geometric series. If the ratio between terms approaches some number, then out at infinity it's acting like you're multiplying by r. That's what we're saying. And if it acts like a geometric series, then maybe we can use these rules, and the answer is yeah, we can use these rules about whether r is bigger than or less than 1. All right, so let's try this with this particular one right here. Use the ratio test, it says, to test for convergence. We should also stop and appreciate the fact that this is neither arithmetic or geometric, but yet we can still think about it maybe as if it's geometric. Let's try. Before we do anything else, we should maybe give the rule. What is it here? I didn't make it too hard for you. Look at that good choral response. Okay. So here we go. This is how the ratio test goes. We're going to compute this r value. It's going to take a little bit of work, but that's not too bad. It's the limit as n goes to infinity of the next term divided by the previous term, excuse me, the current term. So what is the next term? If the current term is called n over 2 to the n, then the next term is n plus 1 over 2 to the n plus 1. Okay, let's just make it really explicit. So that's what we're stacking. N plus 1 over 2 to the n plus 1 divided by n over 2 to the n. By the way, if you do this, and it actually is a geometric series, then what happens here when you do this? Yeah, you get r, don't you? And in fact, there's no need to say limit as n goes to infinity if it's geometric, because it'll just come out to be a constant. N's will cancel out. It'll just be a constant. So you can in some ways talk about this test as being like the general rule. It's even better than like the geometric series test. It's even more general than that, maybe you could say. So I'm going to try and clean this up in ways that feel familiar here. I'm going to flip a fraction here and all that. So I think I get, what do I get? N plus 1 over 2 to the n plus 1 times 2 to the n over n. And this is the fun part, right? You can see what there might be that you can cancel out. What do you see that can be canceled out inside those parentheses? Steven's got it. Yeah, leaving what? And the n plus 1 and the n will just leave as they are for now. And let's just see where we stand right now, at least. We have the limit as n goes to infinity of, up on top, just n plus 1. And on the bottom, 2 times n. Are we ready to evaluate that limit yet? Are you ready?
Yeah.
What is it?
1/2.
1/2. So I think we might be able to be ready to make our conclusion now. But let me just make sure you're really clear on what we just did. This expression, you guys, right here, just bracketed, this expression is a rule that's maybe useful in its own right. If you plug in like 1,000,000 to this rule, what does it give you in brackets? If you plug 1,000,000 everywhere you see an n. Describe in words what that says to us. Yeah, it'll be like 1,000,001 first over something 2 to the 1,000,000 first, right? But what will that give you when you're done and you have done the division here? It'll give you Well, what is this? Compute here. We are doing the ratio test, by the way. It gives you the million first term divided by the millionth term, right? You would say that's like the ratio between the million first term and the millionth term, right? Agree? So what are we saying when we say that as we go toward infinity, the ratio between terms is 1/2? It means that, what do you have to do basically to get from the millionth term to the million first term? Practically speaking, yeah, you're just basically multiplying by 1/2, right? It's not perfectly right, because the rule is not geometric. But what we're saying is out at infinity, it acts like it's geometric. It's basically 1/2. Every time you go from one term to the next, it's basically like you multiply it by 1/2. Out at infinity, at least. Does that make sense? And with that understanding, now it makes sense why this conclusion maybe works. So, since R is 1/2, which is less than 1, the series converges. By ratio test. Okay, so that's the work I'd like to see for the ratio test. Yeah, Tim.
If you write, when you write down all the algebra, could you say therefore the series converges?
You should say, I might give you permission to write like less than 1 over here. How about like less than 1?
Yeah, that is less than 1.
Yeah, I need you to say something about the fact that since 1/2 is less than 1.
Yeah, you have to say, yeah.
Yeah, that's fine. As long as you have each element, you don't have to use the exact wording I'm using. Yeah, Sue.
So you don't need to write out the series again?
I mean, I think it still needs series we're talking about in this particular problem, so I think that's pretty clear, but you wouldn't be wrong to do it. Maybe I should have. Yeah.
This is just being lazy, but you have to write limit n is greater than infinity every single time you
Yeah.
do it.
Yeah, you should write that everywhere you can until you've actually evaluated the limit. Let's do another one. See how we do on this. All right. I gave you the rule. I don't think I needed to, but there it is. Okay. We'll do the ratio test again. The limit as n goes to infinity of the next term, which is just the rule with an n plus 1 stuck in, all over the current term. And I don't know, maybe you can already tell me what you get.
1.
What do you get? What did you say? Sorry, I didn't quite hear you.
1.
Do you get 1? Is that what you get? No, you do, I think. Is that what? Okay. So what does that tell you then? Yeah, that maybe the ratio test wasn't, I just wanted to show you what this feels like when the ratio test comes up inconclusive. Because it might seem pretty cool and powerful, and it is. But there's certain simple series like this one that it comes up inconclusive on, and it's often ones like this one. So does that mean we walk away? No. Maybe we just need to try a different test. Well, how about the nth term test? Well, the terms go to 0, so that's not good enough. Okay. What else do we have? Direct comparison. What would you like to compare it to?
1 over n.
Maybe 1 over n. The only problem there is that it's actually less than 1 over n, and 1 over n diverges. We can't really say anything about this if it's inside of a divergent series, right? So how about the LCT? Yeah, and I think that will work for you. Try the LCT, and you'll see that it does diverge, but we won't write it out. Okay. I just want to make sure you're seeing that, like, there are different tests for different times. The LCT turns out to be maybe the one to use here, not the ratio test. So that's going to be one of your tasks, is distinguishing between those. What, the limit comparison test?
Like what you would start with.
I would stack this rule over 1 over n, or the other way around, and I would show that the limit comes out to there either 5 or 1/5 is what it'll come out to, right? Doesn't have to be 1. Any constant. For the limit comparison test, any constant is fine. Just can't come out to 0 or infinity. Yeah. All right. Well, I would have liked to go back and try it. Maybe you should try that last warm-up problem. We'll see how you do with that factorial. You should be pretty well equipped to go back and do every problem on the homework now. Homework 3 and 4. Is everyone clear on what the homework is? Okay.